Then in your syllabus you have improper integral as your very first topic in the integral calculus. So, today we will start improper integral from the integral calculus section. So, improper integral, as the name itself suggests, that something is not proper. So, when we say proper integral, it usually means that you have integral from a to b f x dx, and your function is continuous, it could be differentiable, your a and b, the endpoints of the interval, they could be finite. So, the entire terms or entire how to say function or the endpoints, whatever involved in this, they are all well defined in a way that nothing is becoming infinite. Now, it may happen that in several situations where you could have that f x is becoming infinite, or your f x can be discontinuous. Or it may happen that either a equals to infinity or minus infinity, or your b equals to infinity or minus infinity. So, something like that, I mean anything that falls into that category, then such type of integrals are called as infinite integral. So, for example, if your a and b are finite, however, your function is becoming infinite at any one of the points or at the end points itself, then in that case the integral is improper integral. If either one of the end points are becoming minus infinity or plus infinity, then that is also an example of improper integral. Your function might become discontinuous within the given range of integration, then that is also an example of improper integral. But mostly we are concerned with the infinite discontinuity. If the function is itself discontinuous within the interval a to b, and if that discontinuity is not infinite, then there is a separate way to deal with those kind of integrals, but we are not concerned with them. So, now we are going to define several types of improper integral, and I will teach you how to evaluate those integrals. So, the very first type in this regard is convergence at the left hand point. So, convergence at the left hand point. So, what does it usually mean is, suppose you are given let a be the only point of infinite discontinuity, infinite discontinuity of a function f, then we say that the improper integral a to b f x dx exists if we have integral a to b f x dx equals to, the trick is to add a little bit epsilon, that means to go away from that point of discontinuity. So, I will write limit epsilon goes to 0 positive a plus epsilon to b f x dx exists. So, if this limit exists, what we are basically doing, suppose if this is your given this is x axis, if this is your given function y equals to f x, and if you are evaluating from x equals to a to x equals to b, suppose if a is the point of discontinuity, that means you have the point of discontinuity at x equals to a, then basically what we are doing, we are evaluating the integral by adding an epsilon let us say something like this. So, this is our a plus epsilon. So, we are getting a little bit away from the point of discontinuity, and then we are evaluating the integral. So, this integral we can evaluate, and once we can evaluate, then we will make epsilon go to 0 afterwards, alright. And why we are adding an epsilon? So, you see epsilon is tending to 0 from positive side. So, that means we are coming to epsilon from right hand side. Otherwise, if you add an epsilon, or if you write it as a minus epsilon, let us say, then what will happen is you will end up being here, and that goes outside of the given interval. So, we do not want that actually. So, we have to stay within the given range of integration, that means a to b, and when we are evaluating the integral at the left hand point where we have the infinite discontinuity, you add an epsilon so that you stay inside the interval, alright. We cannot write a minus epsilon, otherwise we will go outside of the interval. So, that is the first definition. The second one is convergence at the right end point, convergence at the right end point, REP. So, convergence at the right end point usually mean that let B be the only point of discontinuity, of a function f, then integral from a to b fx dx exists if you have limit. So, first of all, let us write the integral equals to limit epsilon tending towards 0 from minus, and let us keep the same notation, epsilon tending towards 0 plus a to b minus epsilon fx dx, if this limit exists. That means, suppose if the discontinuity is at this point, then what we are doing is we are subtracting a little bit epsilon, so that we are at here. So, we again avoided the point of discontinuity, and then we evaluate the integral here, and afterwards we pass the limit, epsilon goes to 0 positive, and whatever is the value, that will be the value of the integral, alright. So, again we cannot do b plus epsilon, because the minute we do b plus epsilon, we will end up here, and that is something we do not want. We do not want to go outside of the interval. So, we want to stay inside the interval a to b, and therefore, in case of right end point, we write a to b minus epsilon, alright. Now, it may happen that you have discontinuity at both the points, and if you have discontinuity at both the points, let us say third example is convergence at both endpoints, convergence at both endpoints. So, suppose you have a function, so let endpoints a and b be the point of discontinuity. Then integral a to b fx dx can be divided from a to c fx dx and c to b fx dx, and then you can write this as limit epsilon goes to 0 positive a minus a plus epsilon to c fx dx plus limit epsilon going to 0 positive integral from c to b minus epsilon fx dx. Now, if those limits exist, then we say that the given integral, improper integral, is convergent. All right. Now, fourth definition, sorry. So, the fourth definition is convergence at infinity. Convergence at infinity, minus infinity and plus infinity. So far up until the third definition, so first, second and third definition, our point of integration, those were finite. So that means none of the endpoints are infinity. However, your function has infinite discontinuity. And then we can define the improper integral, and we can also see how we can evaluate the given improper integral. Now, it may happen that your endpoints become infinity, and then in that case, that is also an example of improper integral, but how do we evaluate it? So the definition goes like this. So let fx, the improper integral, let us say a to infinity fx dx exists if integral a to infinity fx dx can be written as limit t tends to infinity a to t fx dx, which exists. So, if this limit exists, then we can say that the given integral is convergent. If it does not exist, then we say that the given integral is divergent. So, when we are checking the convergence of the left hand point, then we say that if this limit exists, then we say that it is convergent at the left hand point. If this limit exists, then we say that it is convergent at the right hand point. If this limit exists, then we say that it is convergent at both the end points. And if this limit exists, then we say that it is convergent, it is simply convergent. And if it does not, then we say that it is divergent. Similarly, we can define the convergence at minus infinity, which means that integral from minus infinity to b fx dx can be written as limit t tends to minus infinity t to b fx dx exists. And if you have minus infinity to plus infinity, if we have minus infinity to plus infinity, I am going to write in this small space. So, if we have integral from minus infinity to plus infinity, so then we can divide it minus infinity to some c fx dx plus some c to infinity fx dx. Now, if both the integrals exist, then we say that this integral exists, otherwise it is divergent. All right. So, if you have minus infinity to plus infinity, you just divide it at some midpoint where it is not becoming undefined in a way, or it does not have infinite discontinuity. Because if you have divided at a point where it is having infinite discontinuity, then you have to take care of that as well by introducing some epsilon and then calculating that value of the limit, whether it is convergent or not. So, basically using all these definitions to split the interval and then apply the individual definition to calculate the improper integral at one particular endpoint, whether it is finite or infinite. All right. Now, so let me just clean the white blackboard. Just okay. So now we will solve a few examples motivated from this. So our very first example is, so example 1. So here we have to evaluate, find out I equals to integral from 0 to 1 dx by square root of 1 minus x square. What will be the value of this integral, whether this integral is convergent or divergent. So obviously this integral is an improper integral of very first type, where one of the endpoints is becoming infinite, right. So here in this case at the right endpoint, that means when x is 1, this integral is undefined. or it has infinite point of discontinuity. So then what we can do? So first of all, we can write I, which is integral from 0 to 1 dx by square root of 1 minus x square, as limit epsilon going to 0 positive, 0 to 1 minus epsilon dx by square root of 1 minus x square. All right, and 1 minus x square root of 1 minus x square is, we know it is sine inverse x. So we can write sine inverse x integral from 0 to 1 minus epsilon. Now we evaluate. So this one will be limit epsilon going to 0 positive. This will become sine inverse 1 plus epsilon minus sine inverse 0. Sine inverse 0 is 0. So that's we already know. And here when we make epsilon goes to 0, this entire thing will go to sine inverse 1. Now sine inverse 1 is, I hope it is pi by 2, yes. So sine inverse 1 is pi by 2. So although we had the infinite point of discontinuity in the integral, where we could not be able to evaluate the integral, with the help of the trick which we, or the definition which we learned, we can be able to evaluate the integral, and the answer is pi by 2. One can directly write sine inverse x and then substitute 0 to 1, but that is in a way not correct, because the underlying theory is that you have an infinite discontinuity. So you have to take care of that first before you can actually evaluate the integral, and taking care of that is basically writing it in this way. All right. Next we solve one more example. So another example in this regard would be let me take this example, example 2. So we have I equals to integral from 0 to pi d of x by sine of x. What will be the value, or whether the integral is convergent or not? So here we can see that we have in the denominator sine of x, and sine of x is obviously 0 at x equals to 0 and at x equals to pi. So it basically means that we have infinite discontinuity, because our given function is 1 by sine x. So we have infinite discontinuity at x equals to 0 and x equals to pi. It's always better to write that. So solution, here x equals to 0 and pi are the only 2 points of infinite discontinuity. This continuity, you can write infinite discontinuity. So since we have the discontinuity at both the endpoints, we already learned that what we can do, we can write I as integral from 0 to pi by 2 dx by sine x, pi by 2 to pi dx by sine x, and we call this one as integral I1 and this one as integral I2. And now we will evaluate I1 and I2 separately. It may also happen that when you are dividing a given function, when you are dividing a given interval, you may end up having more than 2 points of infinite discontinuity. For example, if you, we will evaluate this, but let's say third example is I equals to dx by, let's say integral from 1 to 4, we have x minus 1, x minus 2, x minus 3 and x minus 4. So now in this case, basically we have 4 points of discontinuity, infinite discontinuity, and therefore here you have to write 4 sub-integrals. So that means we can start from 1 to let's say, in fact it will be more than 1 sub-interval. So basically we can write 1 to 1.5, then 1.5 to 2, so 1 to 2, then 2 to 3, and then 3 to 4, and so this can be written as 1 to 2 plus 2 to 3 plus 3 to 4, and then each one of them can be divided into another subintegral. So like 1 to 1.5, and then 1.5 to 2, then 2.5 to 3, then 2 to 2.5, then 2.5 to 3, and so on. So you see, based on the number of points of infinite discontinuity, we have to divide the given integral into that many subintegrals, in fact more than the number of discontinuities we have here, and then you have to evaluate each one of these subintegrals. So that will be a little bit lengthy and tedious process, but if the question asks you to do that, you have to do that. Okay? Now, let's go back to the second problem. So here we will evaluate I1 individually. So here we see that x equals to 0 is the point of discontinuity. So we can write limit epsilon goes to 0 positive, 0 plus epsilon pi by 2 dx by sin x. Now integral of dx by sin x. So we have 1 by sin x. That means this sin x will go up and will become this one will become sin x. So we can write 2 sin x by 2 cos x by 2. So ultimately if you evaluate this, then it will reduce to limit epsilon goes to 0 positive. So this will reduce to mod of, so this will reduce to log of tan x by 2 integral from 0 plus epsilon to pi by 2. Now tan pi by 2, so this will become tan pi by 4, log tan pi by 4, and log tan 0. So let me just write them separately. So limit epsilon goes to 0 positive, we will have log of tan pi by 4 minus log of tan epsilon. So when epsilon goes to 0, tan will go to 0. So when epsilon goes to 0, this tan of epsilon will go to 0, and therefore log will be undefined. So it does not matter wherever this term is going, since this term is undefined. So this is becoming undefined, or you can say that it is going towards minus of infinity, minus minus plus. So because of this minus sign, this will go to plus. So this entire thing is going to plus infinity as epsilon going to 0 positive. Therefore this integral is undefined. So you don't even have to evaluate the second one, because here you have wrote down this integral I as the sum of two subintegrals. If any one of them is becoming divergent, therefore the entire I will become divergent, because we cannot have sum of one divergent and one convergent integral as a convergent integral. So if any one of them is becoming divergent, then the entire integral will be divergent. If both of them are convergent, then we say that the integral is convergent, and if both of them are divergent, then it is still divergent. All right. So this is one such example where we can implement the concept of separating the limit point, separating the end points, and then calculating the integral. Similarly, if you have more than, in this case, if you have more than 2 points of discontinuity, then you basically write it in this way, and then you separate, since you have point of discontinuity at 1 and at 2, so you divide somewhere half or 1.25, something like that, and then you evaluate the integrals and so on. It may happen that, let's say, if you have x minus 1.5, then you again have to split this one. So it gradually it will increase the number of subintegrals. So depending on the points of infinite discontinuity, your number of subintegrals will gradually increase. And I mean, if you can evaluate them, that's fine, but it might be a little bit lengthy process. Now, let's define or talk about two tests with the help of which we can evaluate a given integral, improper integral. So basically, we will define our first comparison test, first comparison test. So let f and g be 2 positive functions such that f(x) is less or equal to g of x for every x in a given interval a to b. Then first conclusion is integral from a to b f(x) dx is convergent if integral from a to b gx dx converges, and second conclusion is integral from a to b gx dx diverges if integral from a to b f(x) dx diverges. So, basically what it means is, if you have a function f(x) which is lesser or equal to g of x, then integral from a to b f(x) dx will be convergent. So, if integral from a to b gx dx is convergent, in other way it means that if you have a function which is smaller than the other function for every x in a to b, then the integral of this will always be convergent if the integral of this is convergent. So, you have a bigger function whose integral is becoming finite on a same point of integration, same interval of integration, then in that case obviously a function which is smaller than this g of x, that integral will be also convergent. And other way around, if a smaller function, let us say f of x, is divergent, then in that case the bigger function on the same interval of integration will also be divergent. So, that is what it means or it says, and hence the comparison test. Hence the name is comparison test, because we are comparing the two integrals. So, if the this integral is convergent, then this one is convergent. If this one is divergent, then this one is divergent. So, that's the comparison what we are talking about. And second one is, second comparison test is second comparison test. So, let f and g be two functions, be two positive functions on a to b such that limit x going to a positive f(x) by gx is equals to some L, where L is not equals to 0 and it is finite. L is not equals to 0 and it is finite. Then first conclusion is integral from integral from a to b f(x) dx and integral from a to b gx dx both converge or diverge together. Converge or diverge together. That means if you want to evaluate converge or diverge together. If you want to evaluate, let us say whether integral from a to b f(x) dx is convergent or not, then basically we find another function g such that we can evaluate this limit. Now, if this limit becomes finite and also non-zero, then in that case if your chosen integral for g is convergent, then you can say that your original integral which you wanted to check is also convergent. And if your g is if this integral is divergent where it involves g, then in that case your original integral will be divergent. And that is for the endpoint A. If you change the endpoint to B, then in that case we can say that it is converged or diverged together at B. Did I not write A? So, at A. And if you are checking for B, then it will be at B. We can also say something about the limit. So, a limit can become 0 as well. So, let us put a small remark. So, remark. So, the first remark is if L is becoming 0, so the first remark is if L is becoming 0 and integral from A to B gx dx converges, then integral from A to B fx dx also converges. And second conclusion is if L is becoming infinity and integral from A to B gx dx diverges, then integral from A to B fx dx also diverges. That means if your L is infinity and if gx dx is convergent, then it will remain inconclusive, and if if L is infinity and if gx dx becomes convergent, then also it will remain inconclusive. And then we have to look for some other test to verify the convergence of the given improper integral. All right. Now, based on this, we will again solve some examples. Okay, let us start from here. Example 1. So, how do we implement the improper comparison test? All right. So, we will see the application of first comparison test. So, evaluate or verify, evaluate integral from 0 to infinity log of 1 plus 2 sec hyperbolic x d of x. All right. Solution. So, when x is infinity, then obviously it is an example of improper integral. So, what we can do, we can first of all separate this I. So, I can be written as integral from 0 to 1 fx dx and an integral from 1 to infinity fx dx, where fx is log of 1 plus sec hyperbolic x. So first of all, we will check the convergence at 0 and we will check convergence at x equals to infinity. And I would also like to point out what is our sec hyperbolic x. So sec hyperbolic x is 1 by cos hyperbolic x, and this is 2 by e to the power x plus e to the power minus x. This we already know from our usual definition of hyperbolic functions. So that is our sec hyperbolic x, 2 e to the power x. And this can also be further simplified to 2 e to the power x, e to the power 2x plus 1. So let's just write up to here. Now we will check the convergence at 0. So first of all, convergence at 0. So convergence at 0 can be checked very easily. So limit x going to 0 positive, log of 1 plus sec hyperbolic x. So this is limit x going towards 0 positive, log of 1 plus sec hyperbolic x is 2 e to the power 2x divided by e to the power 2x plus 1. So when x is going towards 0, this will be, so there is a 2 here. So there is a 2 here. So 2, so this will be 4, and when x is going towards 0, then this will go, this will go towards 1. This one is 1, so 2, 4. So this will become log of 3. So that means when x is tending towards 0, the integrand itself is finite. So the first integral, that means 0 to 1, is always finite. So therefore, this is a proper integral. We are not concerned about whether it is convergent, what is the limit. What we are basically checking is whether it is a proper integral or improper integral. If it is improper, then whether it is convergent or not. So here in this case, we can see that at the end point x equals to 0, the integrand itself is converging towards a finite limit. So that means if the integrand is finite within the given point of integration, and none of the endpoints are infinite, so this is an example of proper integral. So at x equals to 0, this integral will always converge. Now what will be that limit? That's a different question. That's not we are concerned of. Now second point is convergence at x equals to infinity. So we have to check whether it is convergent at x equals to infinity or not. And in order to do that, we will now take help of some inequality. So basically, the first comparison test involves how good you are at inequalities. All right. So we know that log of 1 plus x is less than x for all x greater or equal to 1. This can be verified. So therefore, log of 1 plus 2 sec hyperbolic x is less than simply 2 sec hyperbolic x. Obviously, here if I treat this x, it's better to write theta so that you can avoid the confusion. So for all theta greater or equal to 1. Now I am choosing theta equals to 2 sec hyperbolic x. Alright. So obviously 2 sec hyperbolic x, if you multiply by 2, then this will become 2 sec hyperbolic x equals to 4 e to the power x, sorry, here it should be e to the power x. So 4 e to the power x, and that will always be greater or equal to 1. Yes. So basically this inequality will always be satisfied. Now if I do integral 1 to infinity log of 2 sec hyperbolic x d of x is less than integral from 1 to infinity 2 sec hyperbolic x d of x. So this is nothing but integral from 1 to infinity 2 e to the power x 2 to 4 actually 2 sec hyperbolic x, so 2 4 basically. This will become 4 e to the power x e to the power 2x plus 1 d of x. Now if I substitute e to the power x equals to some z, then in that case this one will reduce to 4 e to the 4 integral from e to infinity. So when x is infinity, is it? Yeah. So this will be 4d of y square plus 1, and this is less than, I have already written a 4 here, so there is no point of writing 4 here. So this will become 4 e to the integral from e to infinity dy by y square, right. So from here what we have used, y square is less than y square plus 1, therefore 1 by y square is greater than 1 by y square plus 1. So that is what we have used from here to here. Now this is always convergent because this will be minus 1 by epsilon, minus 1 by y, and when y tends to infinity, that limit is finite because y going towards infinity means 1 by y will go towards 0. So this is always convergent, this is a proper integral, and this is always convergent. Well, it is an improper integral, but it will converge. So in that way I meant proper. So this is an improper integral which is convergent. So if I compare this one and this one, then basically the given improper integral, so by comparison test, integral from 1 to infinity log of 1 plus 2 sec hyperbolic x is convergent, because, make sure you write this, because this integral is convergent. And since we have divided the given range of integration 0 to infinity between 0 to 1 and 1 to infinity, and we managed to show that it is proper integral between 0 to 1, that means it is a convergent integral, and we also showed that between 1 to infinity it is also convergent. So therefore, both the sub integrals are convergent, and we can say that the given integral originally, this one, is also convergent. So that is one such example or one such application of improper integral. One such application of first comparison test. I can show you one more example for first comparison test. So another example goes like this. So evaluate or find the value of 0 to infinity cos x by 1 plus x square d of x. So here x equals to 0 is not the point of discontinuity. We have only the point of discontinuity at x equals to infinity, because one of the end points is infinite. So this is an improper integral. Now solution. Now what we will do, let f of x equals to cos x by 1 plus x square. So obviously cos x is less or equal to 1, so we can write fx is less or equal to mod of fx, which is mod of cos x by 1 plus x square, and this one is less or equal to 1 by 1 plus x square, right. And because cos x is less or equal to 1, because mod of cos x is less or equal to 1 for every x. So then I will choose this as g of x. So choosing this as g of x, and this will imply integral from 0 to infinity fx dx, which is cos x by 1 plus x square, is less or equal to integral from 0 to infinity gx dx. Now gx is integral from 0 to infinity dx by 1 plus x square. Now integral of 1 plus x square is tan inverse x, 0 to infinity. Now tan inverse infinity is pi by 2, and tan inverse 0 is 0, so this will be pi by 2. So that means integral from 0 to infinity gx dx is convergent. or you can say that it in some way it is behaving like a proper integral because it is converging to a finite limit, and therefore integral from 0 to infinity f(x) dx by first comparison test is also convergent. So, by first comparison test, FCT, or let us write capital F, capital C, capital T. In the examination, make sure you write the full form. By first comparison test, we can say that integral from 0 to infinity f(x) dx is also convergent, or is convergent. All right, convergent at x equals to infinity, and therefore it is convergent, or it converges in the entire interval 0 to infinity. All right, so these are the two examples motivated from first comparison test. Now we will solve one or two examples from second comparison test, and then we'll move on to our next topic. So, now I will give you one example where we see the application of second comparison test. So, to do that, let me take one more example. All right. So, example 3, I guess. I am not sure which example number is this. But anyways, integral from 0 to pi by 2 sin x by x to the power n d of x. All right, sin x by x to the power n d of x. So, here solution. So, here 0 is the only point of discontinuity. 0 is the only point of discontinuity because at x equals to pi by 2, this is not an improper integral, and also at neither one of the in between points from 0 to pi by 2, it is becoming infinite. All right. So, the only point of discontinuity, 0 is the only point of discontinuity is 0, point of discontinuity. So, 0 is the only point of discontinuity. Now, we will say let f(x) equals to, you will always have to assume f(x) as the given integrand, because if you assume f(x) as something else, then you may not get the same comparison test, second comparison test working for the same integrand or same integral which is given to you. So, the rule of thumb is you always assume f(x) as the given integrand sin x by x to the power n, and let us say we choose g of x. Now, how you choose g of x is entirely up to you, and it comes via practice. So, we are not there is no known formula that based on f(x) you choose some gx. So, how you choose gx is entirely up to you and how good you are at it. All right. So, now we will evaluate the limit at x equals to 0. So, the point where we have the infinite discontinuity. So, f(x) by gx, and this will become limit x going towards 0, f(x) is sin x by x to the power n and 1 by x to the power n minus 1. So, I believe this one will reduce to limit x going towards 0 positive sin x by x, and this is 1. All right. Now, integral from 0 to pi by 2 gx dx, this is 1 which is not equals to 0, and it is also finite. All right, it is also finite. Now, gx dx is equals to integral from 0 to pi by 2 dx by x to the power n minus 1. When we evaluate, we will see that this will be convergent. So, this is nothing but, so again we have discontinuity at 0. So, we can write it as limit epsilon goes to 0 positive, and then when we evaluate, this is epsilon to pi by 2 dx by x to the power n minus 1. So, this will go in the numerator and it will become 1 minus n, and then we add 1. So, this will become limit epsilon going towards 0 x to the power 2 minus n divided by 2 minus n integral from epsilon to pi by 2. Now, when n is becoming, so here we will substitute epsilon, and if n is becoming smaller than 2, then in that case this entire thing will be divergent, right. So, we substitute x equals to pi by 2, it will not create any problem. For x equals to pi by 2, this will remain always well behaved. Now, when x is epsilon, so this will become epsilon to the power 2 minus n, and epsilon is going towards 0. So, that means epsilon is a very small number, and if n is less than 2, then in that case that will come in the denominator, and then this whole thing will become infinite. So, at least you need to have n greater than 2. So, this converges. So, this converges if n is greater than n is less than 2. So, if n is less than 2, then this is a convergent or this is converging. So, therefore, we can say that by second comparison test, integral from 0 to pi by 2 sin x by x to the power n d of x is convergent if n is less than 2. All right. Similarly, we can solve one more example. Let us say we have find the value of, or check whether, find the value or check whether the integral, what is that, 0 to 1 e to the power minus x by x to the power 1 minus a d of x, where a is any real number. So, obviously, here what we can do, we can again take fx as e to the power minus x divided by x to the power 1 minus a, and g of x as 1 by x to the power 1 minus a. So, obviously, we have to check first the limit. So, the first step is limit x tends to 0 positive, because that is where we have the infinite discontinuity. Except x equals to 0, we do not have any other point of discontinuity. So, then we can evaluate fx by g of x, and this will come out to be limit x tending towards 0 positive. Fx is e to the power minus x divided by x to the power 1 minus a, and x to the power 1 by x to the power 1 minus a. So, this will become limit x tending towards 0 positive. Now, since x is tending towards 0 positive, we can cancel out x to the power 1 minus a, and this one will become e to the power minus x. So, this is 1, which is again not equals to 0, and it is finite. Now, we will check what is going to happen to integral from 0 to 1 gx dx. So, this is integral from 0 to 1 gx dx, that means dx by x to the power 1 minus a. So, again we can write that same thing what we did in the previous one. So, we can write limit epsilon tends to 0 positive integral from epsilon to 1 dx by x to the power 1 minus a. So, this will become limit epsilon tending towards 0 x to the power a. So, it will become a minus 1. So, x to the power a divided by a epsilon to 1. Now, again epsilon is tending towards 0. So, if a is less than 1, then in that case, if a is negative, not less than 1, if a is negative, then in that case this will again become this will again tend to infinity. So, that we do not want. So, this is convergent if a is positive, and therefore, by second comparison test we can say that this is convergent if a is positive. All right. So, this is how we prove the convergence of an improper integral using first comparison test and second comparison test. Similarly, we have abundance of examples which we can work out. So, I am pretty sure you may have gotten some problems in your tutorial sheets, in your assignment sheets, and you can see how to solve these problems. All right. So, we will have a 5 minutes break and then we will continue again. All right. So, in the same improper integral, now we are going to learn about two very special type of integral, which are also called as functions, which has also very how to say wide application. So, they are called as beta function and gamma function. They are both examples of improper integral, but we will learn about them in a little bit more general way, and we will also study about their properties. So, first of all, we will define the gamma function. So, we are going to define the gamma function, which is also an improper integral. So, gamma function is defined as let I equals to integral from 0 to infinity x to the power n minus 1 e to the power minus of x d of x be the given integral, then I is convergent if and only if n is positive. So, obviously, this is an example of an improper integral, because at x equals to infinity, first of all we have that one of the limit points infinite, and therefore, this falls under the category of gamma integral. Why it is called gamma integral, I will come back to that point later. So, now we are saying that it is convergent for all n positive. So, now solution. Let f of x equals to x to the power n minus 1 e to the power x. Then here 0 is the point of discontinuity if n is less than 0 less than 1, and infinity is the one of the endpoints, or you can write right endpoint of the integral. So, we have two situations of improperness. So, what we will do, we will first examine the convergence at 0, and then we will examine convergence at infinity. So, we have to check convergence at x equals to 0 and x equals to infinity. So, first of all, let us check at x equals to 0, convergence at x equals to 0. So, when x equals to 0, then we can take, let gx equals to 1 by x to the power 1 minus n. So, then we can evaluate limit x going towards 0 positive fx by gx, and this will become limit which is not equals to 0. Now, we can say, so integral from 0 to 1, basically integral from 0 to infinity, which can be written as fx dx, integral from 0 to 1 fx dx plus integral from 1 to infinity fx dx, where we are checking the convergence at x equals to 0. So, yeah, right here therefore, and so integral from 0 to 1 fx dx and integral from 0 to 1 gx dx converge or diverge together. Right? Basically what we have done, we have point of discontinuity at x equals to 0 and we have one of the endpoints at infinity. So the integral from 0 to infinity can be divided into 0 to 1 and 1 to infinity. At 1 there is nothing happening. So at in the first subintegral 0 to 1 fx dx, what we are doing is we are checking the convergence at x equals to 0, and when x is 0 then we choose the function gx in this fashion and then we evaluate the limit, and the limit is non-zero. So we are saying that integral from 0 to 1 fx dx and integral from 0 to 1 gx dx, they will converge or diverge together. So now we will check the convergence for gx, right. So integral from 0 to 1 g of x dx is equals to integral from 0 to 1 g of x is x to the power 1 minus n, and this is again limit epsilon going to 0 positive, integral from epsilon to 1 dx x to the power 1 minus n. We just evaluated an integral like this and we saw that this integral is convergent for n positive. So this is convergent for n positive, we saw in the previous example. Now step 2 is convergence at x equals to infinity, convergence at x equals to infinity. So at least at x equals to 0, if n is positive, then we have the convergence, alright, of this integral. Now we will check the convergence of this integral. So for any given n and for large values of x, we will have e to the power x greater than x to the power n plus 1. Is it true for n equals to 1 and x equals to 1? So e to the power 1, that means e, which is 2.7 or something, x is 1 and 1 to the power 2. So this is true for x equals to 1, n equals to 1 and so on. So this inequality is true, and therefore this can be written as x to the power n minus 1 e to the power x is less than 1 by x square, right. This can be written as x to the power n minus 1 e to the power minus of x, yes, 1 by x square, exactly. Now I can take integral on both sides, 1 to infinity x to the power n minus 1 e to the power minus x dx, and this is integral from 1 to infinity dx by x square. I will take, so take g of x as 1 by x square, right. So then integral from 1 to infinity dx gx dx will be integral from 1 to infinity 1 by x square d of x. Now 1 by x square d of x is always convergent because you can do limit t tends to infinity 1 to infinity dx by 1 by x square, then evaluate, put the value of x equals to t and then check, this will be always convergent. So this is convergent. This is convergent. So basically for all n. So basically this integral, so this says, so this implies integral from 1 to infinity fx dx is convergent for all n, but the first subintegral has a restriction that it will be convergent only for n positive. So we have the restriction for first subintegral which is n positive, and for the second one we don't have any restriction. So when you combine them together, the restriction of the first subintegral will impose, and you can say that both the subintegrals are convergent for n positive. So we combine this one and convergence of this one, and therefore Therefore, integral from 0 to infinity fx dx, fx is x to the power n minus 1 e to the power minus x, is convergent for n positive. All right. So, that is the convergence of gamma function or gamma integral. And from the notation point of view, so just for the notation, by notation we write gamma n equals to integral from 0 to infinity x to the power n minus 1 e to the power minus x dx for n positive. All right, because after you do the integration, since we are doing the integration with respect to x, after we are done with the integration, we will have a term left only with n, and therefore the right hand side will eventually turn into a function of n. Hence, we are writing it as some function of n, f of n. That f is denoted by gamma. All right. Hence, the term gamma integral or gamma function, because it is ending up being a function of n. Now, based on definition of gamma function, similarly, we can introduce something called beta function, which is also an example of improper integral. All right. Another type of improper integral is beta function. Beta function, and it is denoted by the integral. Some people write capital B m comma n, some people prefer to write beta m comma n. It is up to you. And then the integral is defined as integral from 0 to 1. I have to see the definition. Integral from 0 to 1 x to the power m minus 1, 1 minus x to the power n minus 1 dx exists if and only if m is positive and n is positive. All right. So, here we can see that when x is 0, and then in that case if m is less than 1, so then we have, if m is less than 1, then we have at x equals to 0 a point of discontinuity, because then this one will go in the denominator, and if n is less than 1, then in that case we will again have one point of discontinuity at the right hand point. So, basically 0 and 1 will play the point of discontinuities in this case, and therefore, for the convergence we are saying that this integral will exist if and only if m and n both are positive. Now, the proof follows exactly in the same way, the way we have proven the gamma function or gamma integral. We can try to prove the theorem, prove this function is convergent. So, first of all, so let us just show the convergence of this improper integral. So, the given integral, you can also name it equation number 1. The given integral 1, let us call it 1. The given integral 1 is proper for all m and n greater or equal to 1. So, if m and n are greater or equal to 1, then we have nowhere any point of discontinuity, and this is always proper. So, for us the interesting case is when m and n both are less than 1. All right. So, let m and n, they are less than 1. So, if m is less than 1, then 0 is the only point of discontinuity, only point of discontinuity, and if n is less than 1, then 1 is the only point of discontinuity. So, all in all 0 and 1 are the point of discontinuities when m and n they are less than 1. All right. So, that means for m less than 1 and n less than 1, what we can do, we take half as the midpoint. We take 0 less than half less than 1. So, then we divide integral I as 0 to half fx dx plus half to 1 fx dx, where our fx is this one. This is our f of x, the given integrand. So, let us check the convergence at x equals to 0. So, convergence at x equals to 0. So, let us take fx as, we have already taken fx. So, let us take gx as 1 by x to the power 1 minus m. So, then we can evaluate the limit x tending towards 0 positive, fx by gx, and this will be limit x tending towards 0 positive, fx is x to the power m minus 1 1 minus x to the power n minus 1 divided by 1 by x to the power 1 minus m. So, this will cancel out and this will become limit x tending towards 0 positive 1 minus x to the power n minus 1, and this will become 1. So, obviously, it is non-zero and it is finite. Let us write a comma, and it is a finite number. Now, integral from 0 to half g of x dx. So, this is integral from 0 to half g of x is dx by x to the power 1 minus m. So, again its point of discontinuity is 0. So, we can write limit epsilon going towards 0 positive, integral from half epsilon to half dx by x to the power 1 minus m. So, this will become limit epsilon tending towards 0 positive x to the power m divided by m half epsilon. Now, this limit will become undefined or will tends to infinity or it is convergent only when epsilon is positive. The minute epsilon becomes when m is positive, the minute m becomes negative, then in that case, since epsilon is tending towards 0, it will come in the denominator and therefore, everything will become undefined. So, this is convergent only when m is less than 0, m is positive, m is greater than 0. It will not converge if m is less than 0. Next, we will check convergence at x equals to convergence at x equals to 1. So, if we are checking the convergence at x equals to 1, we will choose fx we have already chosen. So, let g of x as 1 by 1 minus x to the power 1 minus n, and proceeding in the same way, we will find that limit x tending towards 1 positive fx as by gx equals to, no, not 1 positive, 1 negative, and this one will be limit x tending towards 1 negative fx by gx. Ultimately, the value will be 1, which is not equals to 0, and it will be finite. Next, we will check the convergence, which is half to 1 gx dx. So, gx is 1 minus x to the power 1 minus n, and we will see that this is also so here you can write limit epsilon tending towards 0, positive, integral half to 1 minus epsilon dx by 1 minus x whole to the power 1 minus n, and this is convergent if n is positive. So, we have two subintegrals. Where is that? Here. So, we have two subintegrals, and therefore, by second comparison test, this subintegral will again be convergent. So, here we saw that at x equals to 0, we found a gx for which that gx is convergent and the limit is finite. So, by second comparison test, the first subintegral will converge. Similarly, the convergence at x equals to 1 can be guaranteed by the similar argument. That means, we have found a gx for which this integral is convergent. Of course, n must be positive and this limit is finite. So, with the help of them, by the second comparison test, I can say that this subintegral is convergent. But there are two separate conditions. For the first one, we need m positive. For the second one, we have n negative. And because of the two conditions, we take them together. So, we say that both the subintegrals are convergent for m and n positive, which is what we mentioned here, that for m and n positive, this beta function is convergent. So, therefore, we have proven, thus we have proven that beta mn is convergent for all m and n positive. All right. So, in the category of improper integral, beta function and gamma function are the two such improper integral whose convergence is a little bit more important from other integrals compared to other integrals. And beta function and gamma function, they also pop up quite often in applied mathematics, and therefore, they play a little bit important role in the improper integral. Now, we have some properties of beta and gamma function. So, the very first property is what is the value of gamma 1. So, before we write the value, let us write the gamma function and beta function once more. So, integral from 0 to infinity x to the power n minus 1 e to the power minus x dx, where n is positive, and beta function is beta mn equals to 0 to 1 x to the power m minus 1, 1 minus x to the power n minus 1 dx, where m and n, they are both positive. So, the very first property is, what is the value of gamma 1? So, obviously, the value of gamma 1 can be calculated by substituting n equals to 1 here, and then this will become 0 to infinity e to the power minus x dx. Here 0 is not the point of discontinuity. The only improperness we have is at x equals to infinity. So, you make t tends to infinity, and this will become 0 to t e to the power minus x dx. Then when we evaluate, this will become e to the power minus x, then there is a minus here 0 to t, and this will become limit t tends to infinity minus e to the power minus t plus e to the power 0. So, when t tends to infinity, this will go to 0, this is 1. So, basically gamma 1 is 1. All right. Next, we will write one more property. So, one more property is gamma n is equals to n minus 1 factorial. All right. So, that is the second property. So, we know that gamma n is integral from 0 to infinity x to the power n minus 1 e to the power minus x dx. So let's integrate by parts, IBP. So if you integrate by parts, then it will give you minus of x to the power x to the power n minus 1 e to the power minus x evaluated from 0 to infinity plus n minus 1 integral from 0 to infinity x to the power n minus 2 e to the power minus x dx. All right. So when x is infinity, this thing will go to 0. When x is 0, this again go to 0. So this entire thing will go to 0. Now we will have n minus 1 integral from 0 to infinity x to the power n minus 2 e to the power minus of x d of x, right. So this can be further written as integral from 0 to infinity x to the power n minus 1 e to the power minus x dx. Now by definition of gamma function, this is gamma n minus 1, right. So we can write n minus 2 times gamma, no, n minus 1, this is again n minus 1, gamma n minus 1. All right. Again we can do the same integration by parts for gamma n minus 1, and we'll end up having n minus 1 times n minus 2 times gamma n minus 2. So if we keep on doing dot dot, then we will get gamma n equals to n minus 1, n minus 2 dot dot and so on, 2 and then gamma 1, right. But gamma 1 is 1. We have just calculated gamma 1 is 1. So this can be written as n minus 1, n minus 2 dot dot 2 times 1, which is basically n minus 1 factorial. If you substitute n equals to 1, since 0 factorial is 1, this is also clear from this relation also, that gamma 0 is 1. We have some properties of beta function as well. There are like many properties, but I am just going to write down only few of them, and rest of them you can look into any book and try to prove them. So the third property is about beta function. So beta mn equals to beta nm. That means you can change m and n indices, and it will be same beta, the value of the integral will be same, right. So we know what is our beta mn. Beta mn is integral from 0 to 1 x to the power m minus 1 minus x to the power n minus 1 d of x, where m and n they are both positive. So we'll substitute x equals to 1 minus y. So this will give dx equals to dy with a negative sign. So therefore our beta mn will become integral from, so when x is 0, y is 1, and when x is 1, y is 0, right. Better to write y here. Then x is 1 minus y. So this will become 1 minus y to the power m minus 1, and this will be y to the power n minus 1 d of y, and I will put the negative sign here. So I can interchange the integral, and therefore this will be y running from 0 to 1 minus y to the power, or I can write y to the power n minus 1 minus y to the power m minus 1 d of y. The reason why I can change is, there is a little theorem which says that integral from a to b fx dx equals to minus b to a fx dx. This is a very known result in integral calculus. That is the same property we have used here. All right. Now this is y 0 to 1 y to the power n minus 1 minus y m to the power m minus 1 dy. Y is just a variable, so it doesn't matter whether you are choosing x or you are choosing y. It will still be the same, the formula for the beta function would still be same. Now you can compare, instead of y, instead of x we have y, instead of n we have m, instead of m we have n. So this is nothing but your beta n comma m. By definition, you can write by definition. we can also transform the definition of beta function into cos theta and sin theta. So, fourth property is, this is third property, this is fourth property, beta mn equals to 2 times integral from 0 to pi by 2 cos to the power 2m minus 1 theta and sin to the power 2n minus 1 theta d theta. Alright. So, this is very simple. You put x equals to cos square theta in your beta function. So, this is nothing but dx equals to minus of 2 cos theta sin theta d theta. So, therefore, our beta function will reduce to integral from when x is 0, theta is pi by 2, when x is 0, theta is pi by 2, and when x is 1, theta is 0, and this whole thing will become x to cos to the power 2m minus 1 theta, 2m minus 2 theta, sorry, 2m minus 2 theta, and sin to the power 2n minus 2 theta, then cos theta, sin theta, d theta, and there will be a minus at the front with a 2. So, there should be a 2 also, and this entire thing can be written as 0 to pi by 2 cos to the power 2m minus 1 theta sin to the power 2n minus 1 theta d theta, which is what we wanted to prove here. And from here to here we have used this formula. All right. Similarly, there is one more formula about beta function and trigonometrical function. So, another formula is this one was 5. So, half of beta p plus 1 by 2 q plus 1 by 2 is equals to integral from 0 to pi by 2 sin to the power p x and cos to the power q x dx, where p is greater than minus 1, q is greater than minus 1. This you can again prove by substituting x equals to cos square theta in your beta function and then proceed as usual. This is consider it as a assignment or a. So, there is nothing new to prove here. The sixth formula is, or the sixth relation is, connection between beta function and gamma function. So, relation between beta and gamma function, relation between beta and gamma functions. So, the relation is beta mn equals to gamma m times gamma n divided by gamma m plus n. The proof might be a little bit, the proof is a little bit lengthy, so we are not concerned with the proof, but this is a very important relation to know. So, this is a very vital relation. However, the proof is not in your syllabus, so we will just omit the proof, but we will see one very good application of this formula. So, one application is example. So, what is the value of gamma half? How do you calculate the value of gamma half? So, in order to calculate the value of gamma half, let us put m equals to n equals to half in formula 6. In formula 6. So, if I substitute gamma m and n both half, then this will be gamma half divided by gamma 1. So, this will become gamma half divided by gamma half plus half, which is 1. So, gamma half divided by gamma 1. Now, this is equals to your beta function. Your beta function is, remember we have chosen m and n as half. So, here half and here half. So, this will become integral from 0 to 1 x to the power minus half 1 minus x to the power again minus half d of x. And this will become integral from 0 to 1 dx by square root of x times 1 minus x. Now we put x equals to sine squared theta. So if you substitute x equals to sine squared theta, this is dx and this is 2 sine theta cos theta d theta, and therefore everything will reduce to gamma half whole square. Since gamma 1 is 1, so I am not writing that in the denominator, and this will reduce to integral from 0 to pi by 2 sine theta cos theta d theta. Square root of sine squared theta is simply sine theta, and square root of 1 minus sine squared theta is cos squared theta, and then square root is gone. So, this is cos theta. So, they will just cancel out. We will have 2 integral from 0 to pi by 2 d theta. So, this is nothing but 2 times pi by 2. So, ultimately pi, and therefore, we can say gamma half is square root of pi. So, the value of gamma half is square root of pi, and you can also say that from here, not only that, you can also say that beta half is also pi. Okay? So, beta half is pi and gamma half is square root of pi. So, this is one very useful application of connection between beta and gamma function. I am going to write one more relation about gamma functions, which is also quite important. It is called Legendre duplication formula. So, maybe you can write the whole term. So, Legendre's duplication formula. So, the Legendre duplication formula is nothing but square root of pi gamma 2m equals to 2 to the power 2m minus 1 gamma m times gamma m plus half, where m is positive. So, m is greater than 0. So, this formula connects gamma 2m with gamma m, all right. And again the proof is not in your syllabus, so we will just skip the proof. However, we will see again one very good application of this result. So, one very good application of this result is to find out the value of, so exercise 2, let us say exercise 2. So, we want to calculate what is gamma 1 by 4 times gamma 3 by 4. What is the value? All right. So, the solution goes like this. So, let us take m equals to 1 by 4. So, if I take m equals to 1 by 4 in the duplication formula, then my formula will reduce to square root of pi gamma 2 times 1 by 4 equals to 2 to the power 2 times 1 by 4 minus 1 gamma 1 by 4 and gamma 3 by 4. So, I have already got the terms for which I need to calculate the value, and therefore, this will become gamma 1 by 4 gamma 3 by 4 square root of pi gamma half divided by 2 to the power 1 by 2 minus 2, so minus half. So that means this will become square root of 2 square root of pi times gamma half. So this is square root of 2 times pi. So this is the required value of gamma 1 by 4 times gamma 3 by 4. All right. So we'll stop here today, and in the next class we will continue with some more examples on gamma and beta function, and then we'll move on to our next topic, which is double and triple integral. So the reason why we started with integral calculus is that I have covered up to a very good portion of vector calculus. So in vector calculus, the only thing which you have left is the line integral, volume integral, and surface integral. So that we will cover in the following lectures, which will probably take only one lecture to cover. And since we have a whole syllabus of integral calculus left, I started with the integral calculus, and hopefully in next 3 or 4 lectures that will also be covered. You can look into assignments and solve the problems, and if you have any doubts, you can send me the email and I will try to answer. All right, see you in the next class.